Hi everyone. So this is the Internet Ecosystem and Evolution series of seminar series, and in this particular occasion and the next one, what we're going to deal with is the large-scale structure of the Internet. So we basically already discussed the Internet as the network of networks, and we're going to just give a close definition of what we mean by the networks, whose connection into who's connecting into a single large-scale global internetwork makes up the internet. We're going to call these the autonomous systems or the ASes, and we're just going to describe the typical autonomous system, which is the internet service provider. We're going to give a couple of taxonomies to classify ASes according to different criteria. We're going to give the usual access edge core separation. That's one of the evergreen taxonomies of large-scale communications networks. And then we are going to start to delve into a very important detailed description of the internet service model, which basically is a simple way for us to understand the types of relationships that can happen and that can occur between different autonomous systems that recall make up the internet, and we'll start to define one of the most important elements of this service model, the so-called transit service. We're going to just give the definition and notation and go into a couple of details into the way a customer AS actually connects to the transit AS in the transit service. A couple of details about addressing, routing, etc. But first, the internet architecture. So the internet is the network of networks. This is maybe a little bit of the pulp fiction sort of definition of the internet. But in fact, what happens is that there are lots of networks which are in themselves can be very complex and can have non-trivial internal structure. These networks are actually connected to other networks, and these sort of subnetworks, which are not to be confused with the subnets in IP routing. These are actually the ones that actually connected into this large-scale topology that you can see here on the right. This is the large-scale structure of the internet. Okay, so basically we are talking about a couple of thousand networks, 50, or today it's much more of like 60,000 networks, which are the networks of different stakeholders like internet service providers and academia, enterprise networks, governments, military campus networks, all sorts of different networks which are in themselves can be highly complex, internally structured networks. These are connected into a common infrastructure, and we call this particular common infrastructure the internet. So we're talking about 10 billion connected devices, which is a lot. Roughly half of the world is actually connected these days into the internet, and newcomers are arriving in masses. And beyond $100 billion US business revenue, this is a highly conservative estimate on the business value that's actually created on the internet. So what are these networks that actually make up the internet? Again, the internet connects the networks of providers and university campuses, telcos, all sorts of different stakeholders, all sorts of different organizational units into a unified network of networks. Every stakeholder in this large-scale internet playground actually manages and administers his or her own network autonomously, completely independently from the rest of the actors. So in fact, an autonomous system in itself, because we are going to just call these individually managed networks that make up the internet as autonomous systems, each of these autonomous systems is managed independently from the rest of the actors. It does not even need to run IP routing as long as on the border gateway that it uses to connect to the rest of the internet, it speaks IP to the rest of the internet. So again, these networks are called the autonomous systems, And this is a collective name of all these different sorts of stakeholder networks, like service providers in universities, military, telcos, government networks, etc., which make up the internet. An autonomous system is basically a set of hosts and routers and networks that a particular organizational unit owns and administers as a unit. So this is the first part of the definition. And the second part of the definition is that an autonomous system must also be something which exposes a unified routing policy to the rest of the internet. Now we can sort of imagine what the first part of the definition means. For instance, if we think about the local intranet or the network of the Budapest University of Technology and Economics, the BME net. This is basically a typical autonomous system. It connects a couple of all the buildings of the university that are scattered throughout the campus into a common network, and this is a sort of internal network or an intranet that in itself contains lots of hosts and routers and switches and network devices and all sorts of different components that make up a network, which is in itself is a highly complex network. And this BME net is basically seen by the rest of the internet as a single autonomous system, and because it is the BME that actually operates, owns, and administers this network as a unit. The second part of the definition, what does it mean that an autonomous system exposes a unified policy to the rest of the internet? This is something which we are going to describe in more detail in a couple of slides later. What's very important to know about autonomous systems is that each one is actually identified by a single, unique, centrally administered autonomous system identifier. This is a 32-bit unsigned integer value that uniquely identifies one particular autonomous system that connects to the internet. So here's a simple setup. In this particular very small little internet, we have 3 autonomous systems, AS1, AS2, and AS3. These are actually connected into an internetwork. AS1 contains R1 and R2, which are border routers in or so-called autonomous system border routers in this setup, because these are the routers that AS1 uses to exchange traffic with the rest of the autonomous systems in this internet. And it also has some Ethernet backbone and a couple of hosts, like C1 and C2, which are the actual terminals that we want to connect to the internet. What's very important to know about autonomous systems is the following. First, the complexity of an autonomous system can range from a single router, a single border router, all the way to these complex network topologies that we see in BMEnet. And the second important thing to know here is that the demarcation line between two autonomous systems, which is basically the line of, or the boundary between the autonomous systems, always falls to a link between border routers. So it never exists within routers. It never happens that a demarcation line between two autonomous systems divides a single router into two, like for instance these two interfaces would actually just look or belong to a different autonomous system than this particular autonomous system. This is not allowed in the internet. The separation always occurs on a particular link between border routers and not inside routers. Here are a couple of examples for autonomous systems. Of course, a typical example is the internet service provider. So although these types of autonomous systems, these are actually the actors on the internet which provide internet services, access services to individual subscribers and small enterprises. Like here we have Comcast as a typical example, which has the AS ID 6161, or Telenor Hungary, which is a Hungarian internet service provider. The second very important example of autonomous systems is campus networks. A campus is typically an organization which has lots of or many buildings, which buildings are actually just or just located on a single geographical location, like in a campus, and there is a network that connects these buildings and all the stories and all the all the different departments that actually exist in these buildings into a single network. And then this particular network, this campus network, is connected to the rest of the internet. Again, a good example is BMEnet with the AS identifier 256467, or Harvard or MIT. They all have very small autonomous system identifiers, which means that they were very fast to actually connect to the internet. Or here is, for example, ACS, the UCSD, which again has its own autonomous system identifier. The third important actor in this field is enterprises. So these are businesses like IBM or Apple. These again typical examples of autonomous systems where a particular building, an office building, or an entire campus of an enterprise is collected into an autonomous system and switched, connected to the internet as a whole. And then there is the fourth typical example is a global service provider. We are going to just define what we mean by a global service provider. Here is, for instance, Sprint, which is very notorious of actually providing its services on lots of different ASes and AS identifiers. But these ASes that we enumerate here are all operated by a single operational unit, and we can see that the mapping between organization units and autonomous system identifiers is not one-to-one. One particular organization unit can actually operate lots of independent autonomous systems, but one particular autonomous system is always operated by a single operational unit, and that's why our definition of autonomous systems is a little bit loose. That's why maybe a little bit better definition would be that an autonomous system is something which has its own unique autonomous system ID. We have to understand a little bit about intra and interdomain AS, intradomain and interdomain routing, because this is a recurrent concept in this context, which very frequently raises a couple of questions. So the internet routing system handles an AS as a unity. So usually all IP prefixes owned by a single AS get the same treatment in the internet. Again, we are going to just describe what we mean by this assumption. But what's very important is in this context is that the fact whether or not a particular autonomous pair of autonomous systems can communicate through a single intermediary is defined by the so-called routing policies, and the way we actually the way these routing policies are then actually converted into internet routes. This is done by the routing protocols on the internet. These are the routing protocols that somehow embody the routing strategies and the business interests of all the autonomous systems in the internet, and convert these into actual forwarding passes, which will then later be used to forward actual packets between different autonomous systems. Now, the routing protocols themselves, there are two different types. One is called the IGP, or the Interior Gateway Protocol. This is the intradomain routing protocol of the internet, which typically runs inside a single AS. So any two hosts, any two routers connected to a single autonomous system, the connectivity and the reachability between them is actually ensured by the IGP. Typical examples are OSPF or RIP. We know all these. If you know such intradomain routing protocols from your earlier studies, then it is cool. We are not going to delve too much into them. If you don't know them, please make a little bit of reading about IGPs on the Wikipedia. The other very important class of routing protocols is the types of routing protocols that route between or that function and operate between autonomous systems. So this is the set of routing protocols which create the connectivity between different autonomous systems. Intradomain routing protocols run inside a single autonomous system. Interdomain routing protocols run between different autonomous systems. There is also a collective term to describe these interdomain routing protocols. This is called the Exterior Gateway Protocol, EGP, but this collective name does not really make too much sense because there is only just one typical example of interdomain routing protocol. This is BGP. This is the de facto routing protocol, interdomain routing protocol of the internet. Still, we have this collective name of the EGPs. Let's try to delve a little bit more into what we mean by policy unit and what that particular definition of autonomous systems providing a single routing policy unit for the rest of the internet means. In this particular little example, we have 4 autonomous systems: AS1, AS2, AS3, and AS4. AS3, for instance, contains these 2 hosts, C2 and C3, and they are connected through a border router to the rest of this little internet. AS1 contains only a single router, and this is true for the rest of the for the autonomous systems, except AS2, which also has another host. As we can see in this figure, we have a direct link between AS1 and AS3 in this example, which makes it very probable that these particular autonomous systems will exchange traffic on this particular direct link. Now, what happens when this link actually fails? What we see is that direct physical connectivity between AS1 and AS3 terminates. In this case, there is no way to reach any 2 hosts in AS3 to reach any 2 hosts in AS1, except if we traverse other ASes and the network infrastructure of other autonomous systems. So in this particular example, there is AS2 which provides connectivity between AS1 and AS3, despite of the fact that for this particular connection it needs to ensure that corresponding resources in its own network are actually available. In these cases, we can imagine that AS2 has economic incentive to actually provide this connectivity between AS1 and AS3, and this is actually indicated in this figure with this green arrow. So AS1 and AS3 is allowed to communicate through AS2, but in this particular example, AS2 denies access between AS1 and AS4 because we can easily imagine that its economic incentives might be against to provide local resources to ensure this flow of traffic in the network. What we mean by policy unit in this particular example is that whenever there is a routing policy that allows access between AS1 and AS3, it pertains to all the hosts and all the routers and all the IP addresses that are assigned in AS3 and AS1. So if C2 is allowed to communicate on this route through AS2, then most of the times it is also true for AS3, because AS2 actually just handles all of the hosts in AS3, the entirety of AS3 as a single policy unit. The routing strategies and the decisions whether to allow or to block traffic between 2 particular ASes is done at the granularity of autonomous systems and not at the granularity of individual IP addresses or IP hosts. We've seen a first taxonomy previously, where we actually classified autonomous systems into different types based on the type of the organizational unit that actually operates the particular AS, like service provider networks and campus networks, enterprise networks, etc., etc. This other taxonomy takes a different dimension. In this particular taxonomy, we are going to classify different types of ASes based on their traffic profile. The first important class in this taxonomy is the content AS, which is basically a content provider AS. For instance, YouTube, Netflix, or Hulu, these large video streaming services are typical content providers. In these particular networks, the ingress traffic, so the traffic that flows into the network, is very small compared to the amount of traffic that flows outside of the AS, because most of the time people actually download videos from YouTube. So this download traffic, which goes in egress direction out from YouTube's networks, dominates the ingress traffic, so the video uploads to YouTube. So these are typically the content provider ASes whose egress traffic is dominant over ingress traffic. The direct opposite is the eyeball AS, where content consumption is typical instead of provision. So in this particular example, a typical ISP is usually that serves a huge base of customers, like millions of customers who usually just watch YouTube traffic, but locally generate and upload small traffic to the rest of the internet. These are the typical eyeball ASes. The name comes from the fact that these are the types of ASes that contains the customers or the eyeballs. So in this particular case, in eyeball ASes, it is the ingress traffic, so into the AS traffic, that dominates the egress traffic. And we can basically just summarize the role of the rest of the internet. So everything that is not content and not eyeball is the type of the collection of all the infrastructure that is needed to collect to connect content to eyeballs to content with the smallest possible latency possible. The main infrastructure that connects eyeballs to contents is the transit AS, which basically an autonomous system that provides global transit between any two ASes in the network, because it owns a third-byte network infrastructure. Typical examples are Cogent or Level 3 or AT&T's networks. The typical example of a transit AS does not generate traffic inside the AS and does not consume traffic inside the AS. It merely exists to transfer traffic between two remote ASes. So what enters the network usually just flows out at another point. This is the typical transit AS whose traffic profile is not dominated by ingress or egress traffic either. Fourth interesting actor in this field is the content delivery networks, which is basically, we can imagine Akamai or Cloudflare as the combination of content provider and the global transit provider. The other taxonomy, so we've seen a taxonomy that was related to in the dimension of the type of organization that operates an AS. Then we've seen a taxonomy based on the traffic profile of an AS. And this third taxonomy is about a classification based on the actual location of the AS in the internet large-scale structure. This is the venerable edge access core separation that predates the internet and goes back to the telephony networks and even more ancient telecommunications networks. Then the edge is basically all the end hosts that use the services of the internet, and the access concentrates the traffic of the edge into the core, and the core is a huge and large-scale traffic exchange mechanism that exists only to exchange traffic between any two access providers. So a couple of details about the edge. This is the collection of end devices, terminals, hosts, desktops, laptops, mobiles, whatever, everything that we use to generate or consume traffic, and all the ASes that host lots of devices like this. A typical example is the Soho and the Enterprise, which is essentially a Soho is a small office, home office network, where a small office is a small enterprise that contains only a couple of end hosts, or home offices, for instance, are a home network that connects mobile devices and smart TVs and laptops and whatever into a single Wi-Fi network. This is the typical Soho environment, but all other examples for edge are industrial complexes, data centers, which become increasingly more important actors in the internet edge, and also the mobile mobile core networks that provide access to mobile subscribers to the internet. The access network is the network infrastructure that concentrates the traffic from millions and millions of end devices into the internet core. So the large-scale traffic concentration, and of course, in the other direction, traffic demultiplexing occurs. Important concepts here are the notion of the access router, which is typically the first IP router that is encountered by an IP prefix as it travels from the end device to the rest of the internet, and the access link that actually just connects the edge network to the access router. Two important notions here is a CPE, or the customer premises equipment. This is typically an ISP-owned terminal that is located at the customer side, and whose role is, or whose responsibility is to connect the customer sites to the rest of the internet. Typical example is when we use an internet service provider, and then the internet service provider typically provides us with a CPE, which is basically say a line termination or cable modem and a simple Wi-Fi router. Together, these are typically provided by the service provider and provides access to the service provider's infrastructure, and to the home network or the SOHO network. It provides access to this access network. Other important notion here is the demarcation line, which is basically the separation between the customer network and the service provider network, and this is to actually decide the disputes between the different actors. We're not going to details on the typical access networks, the dial-up networks, which is service provisioning on top of the plain old telephony service. This is less and less relevant these days. DSL is the new incarnation, or the modern incarnation of dial-up access. Cable TV providers are an important access provider, a class of access providers in the market, and we see more and more proliferation of fiber to the anything type of accesses, where fiber to the anything can mean fiber to the home, where the actual optical cable is brought all the way into the premises of the customer. Fiber to the premises, where they actually just fiber comes to the building, and from there copper access is provided to the individual apartments. The most important technology to remember is passive optical networking. Another typical access network is campuses, or enterprise or campus access. Enterprise is the collective name of businesses, corporates, facilities, factories, multinationals, everything like that. So basically every business may in itself operate an internal network, which can be a very complex network in itself, and the types of ASes are called the enterprise ASes in this taxonomy. Campus networks, as we've mentioned, is a site consisting of multiple buildings, education, military, government, etc., etc. Here we can see university campus Ethernet access network where the different departments connect to different switches and different VLANs into a single infrastructure, and that allow access to the rest of the internet through a campus access router. Mobile access, very important actor in these days. They say that most of the consumption of the web now occurs over mobile devices, tablets, and the mobile phones. So this is again an important actor. The third important actor in the access or part in the edge access core separation is the internet backbone, or the internet core. We've seen that the access concentrates the traffic of the edge to the internet core, and the core is in itself made up of high-performance, ultra-efficient routers connected into a dense mesh topology, whose sole responsibility is to exchange traffic between different access providers. This is the most important segment of the internet by a large margin, so this is going to be our main topic in the rest of this course. Let's see a typical AS like a typical ISP, just for us to maybe have a mental map or a mental picture of what's going on. When we are talking about an ISP, the ISP is of course a typical autonomous system. This is an internet service provider. Most of us actually have a contract with one ISP or the other to actually connect to the internet. The main profile is actually providing two-way internet access to a large customer base, to individual customers, small office, home office customers, enterprises, etc. Throughout the decades that we've had ISPs with us. Lots of auxiliary services have been caught up by ISPs. We can have domain name registration. They provide domain name registration for demanding customers' emails, cloud storage, server colocation, etc., etc. The typical ISP network, the ISP autonomous system, is made up by multiple POPs. Now, what we mean by a POP, the POP is an abbreviation of the point of presence. This is basically a set of routers, switches, so basically network equipment that is operated by an ISP, so owned and operated by an ISP at a single physical location. Like for instance in a data center, and this is actually the network infrastructure that the ISP uses to provide service access to the rest of its network services. Let's try to maybe make more sense of this a little bit vague definition. Here is a global ISP or a schematic diagram of a mobile ISP. In this particular, of course, hypothetical ISP operates two access networks. We imagine that in Paris, the ISP provides cable access to a largish customer base. If this is the case, then the ISP, of course, needs to operate a couple of network equipment at the Paris location. So it basically means that there is a data center somewhere in Paris where an access concentrator and at least a border router is located, which together provide local service access to these cable subscribers. Also, let's just suppose that our hypothetical ISP provides Ethernet access to small enterprises and also mobile access to individual subscribers. In New York, again, in order to do that, it needs to operate a couple of network equipment in the New York location. So it again rents some facilities in a data center and puts a couple of network equipments there to provide these access services to its customers. Now the rest of the ISP topology, so this is the ISP access network, the rest of the ISP network, which is basically called the POP or the core, consists of different POPs which are located by different, which are basically just network equipment at different locations throughout the world, which provides connectivity between the different access facilities of the ISP and the rest of the internet, and of course between these access networks as well. So in this particular example, our global ISP has a POP in London, in Shanghai, and Amsterdam. And in Shanghai and in Amsterdam, it actually operates autonomous system border routers that are used to connect the ISP's network to the rest of the internet.